Hello and welcome to a new episode of Cosmic Mysteries. In this episode we're gonna talk about fascinating topic of space-time and its role in shaping our understanding of the universe. The relationship between space and time is one of the most profound and mysterious aspects of our universe, and it's have been the subject of intense study and exploration for centuries. In 1915, Albert Einstein published his theory of general relativity, which fundamentally changed our understanding of space-time and gravity. General relativity revolutionized our understanding of the universe by showing that space and time are not separate entities, but are instead inextricably linked and woven together in a fabric known as space-time. In this documentary, we will dive into a fascinating world of the space-time and explore the impact of general relativity on our understanding of the universe. From the curvature of space-time caused by massive objects, to the role of general relativity in shaping our understanding of cosmology and the origin of the universe, we will cover it all. We will also examine the intersection of general relativity and quantum mechanics, and the potential for a theory of quantum gravity, as well as the impact of general relativity of our understanding of the nature of time and causality. Sit back, relax, subscribe if you like this content, and get ready to explore the incredible world of space-time.
Albert Einstein was a German-born theoretical physicist who is widely regarded as one of the most influential scientists of the 20th century. He was born in 1879 in Ulm, Germany, and later moved to Switzerland where he received his education. In 1915, Einstein published his theory of general relativity, which fundamentally changed our understanding of space-time and gravity. Prior to this, the prevailing understanding of gravity was described by Isaac Newton's theory of universal gravitation, which described gravity as a force that acted between masses. Einstein's theory of general relativity, however, challenged this view by showing that gravity is not a force, but instead is the result of massive objects warping space-time. According to general relativity, massive objects cause space-time to curve, and this curvature affects the path of other objects moving through space-time. To put it simply, general relativity says that space-time is like a fabric that is warped and distorted by massive objects, and this warping affects the path of other objects moving through space-time. This warping is what we experience as gravity. Einstein's theory of general relativity has been confirmed through numerous experiments and observations, including the famous 1919 eclipse expedition where measurements confirmed that light was bent by the gravitational field of the Sun, just as predicted by general relativity. According to general relativity, space-time is not a static and unchanging entity, but instead is a dynamic and constant changing fabric that is warped and distorted by the presence of massive objects. This warping of space-time affects the path of other objects moving through it and is what we experience as gravity. In addition to its role in shaping our understanding of gravity, the concept of space-time also has implications for our understanding of the structure of the universe. It has led to new ideas about the nature of black holes, the Big Bang, and the fate of the universe. Furthermore, the concept of space-time has also been incorporated into other areas of physics, including quantum mechanics. Furthermore, general relativity has also had an impact on our understanding of the Big Bang and the origin of the universe. The theory predicts the existence of cosmic background radiation, which has been observed and provides strong evidence for the Big Bang theory. Since its inception, the theory of general relativity has been subject to numerous tests and experiments to confirm its validity. Over the years, these tests have consistently supported the predictions of the theory, providing strong evidence for its accuracy. One of the earliest confirmations of general relativity was the famous 1919 solar eclipse experiment, in which the bending of light by the Sun was observed exactly as predicted by the theory. This experiment provided the first experimental evidence for the curvature of space-time by a massive object. Another confirmation of general relativity came from the observed precession of the orbit of the planet Mercury. According to Newton's law of gravitation, the precession of Mercury's orbit should have a certain value, but observations showed a different value. The theory of general relativity correctly predicted this difference, providing further evidence for its accuracy. In addition, the theory of general relativity has been confirmed by the observation of gravitational lensing, in which the light from distant galaxies is bent by the gravitational pull of massive objects between the galaxy and the observer. This phenomenon is exactly as predicted by the theory of general relativity. Another important confirmation of general relativity came from the observation of binary pulsars. Binary pulsars are two neutron stars orbiting each other, and the motion of these stars provides a laboratory for testing the predictions of general relativity. Observations have confirmed the predictions of the theory, including the emission of gravitational waves and the decay of the orbit of the binary pulsars over time. Finally, the theory of general relativity has also been confirmed by the observation of cosmic background radiation, which provides strong evidence for the Big Bang theory. This radiation is exactly as predicted by the theory of general relativity, providing further confirmation of its accuracy. In conclusion, the theory of general relativity has been confirmed through numerous experiments and observations over the years. These confirmations have consistently supported the predictions of the theory, providing strong evidence for its validity and accuracy.
Albert Einstein is widely regarded as one of the greatest scientists of all time. Born in 1879 in Ulm, Germany, Einstein showed us early aptitude for mathematics and physics. At the age of 16, he enrolled in the Swiss Federal Institute of Technology in Zurich, Switzerland, where he eventually earned his PhD in physics. Einstein is best known for his theory of general relativity, which revolutionized our view of gravity and cosmos. Prior to Einstein, the prevailing view of gravity was described by Isaac Newton's law of universal gravitation, which stated that gravity was a force that acted between masses. Einstein, however, saw things differently. He believed that gravity was not a force, but rather a property of space-time itself.
In 1915, Einstein presented his theory of general relativity, which stated that massive objects cause space-time to curve, and that this curvature is what causes objects to experience the sensation of gravity. According to general relativity, the closer an object is to a massive body, the more space-time will curve, and the stronger the object will feel the pull of gravity. This theory was confirmed through various experiments and observations, including the famous 1919 solar eclipse experiment, which showed that light was indeed bent by the gravitational field of the sun. General relativity had a profound impact on our understanding of the universe. It explained not only the motion of celestial bodies, but also the behavior of black holes, the expansion of the universe, and even the existence of gravitational waves. Moreover, it provided a framework for understanding the behavior of time and causality. Aside from his work on general relativity, Einstein made numerous other contributions to the field of physics. He developed the theory of special relativity, which describes the behavior of objects moving at speeds close to the speed of light. He also made important contributions to the development of quantum mechanics, the theory that describes the behavior of particles on a very small scale. In addition to his scientific achievements, Einstein was also a humanitarian and pacifist. He immigrated to the United States in 1933 to escape Nazi persecution and became a vocal advocate for peace and civil rights. He was offered the presidency of Israel in 1952, but declined the offer. Einstein passed away in 1955 at the age of 76, but his legacy lives on. He remains an inspiration to scientists and a symbol of human ingenuity and creativity. His name is synonymous with genius. According to the Big Bang theory, the universe began as a singularity, a point of infinite density and infinite temperature, and has been expanding and cooling ever since. The theory of general relativity provides a framework for understanding the evolution of the universe, including its expansion and cooling. Another impact of general relativity on cosmology is the understanding of black holes. Black holes are regions of space-time where the gravitational pull is so strong that nothing, not even light, can escape. The theory of general relativity provides a detailed description of black holes, including their properties and behavior. General relativity also plays a key role in our understanding of the structure and evolution of the universe. According to the theory, the universe is composed of matter, radiation, and dark energy, which interact through the curvature of space-time. This understanding has provided insights into the formation of galaxies and large-scale structure, as well as the evolution of the universe over time. Finally, general relativity has also had an impact on our understanding of time and space. According to the theory, time and space are not separate entities, but are instead combined into a single entity, space-time. This view has challenged our traditional understanding of time and space, and has provided new insights into the nature of the universe. In conclusion, general relativity has had a profound impact on our understanding of cosmology and the origins of the universe. The theory has provided a framework for understanding the evolution of the universe, the properties of black holes, the structure and evolution of the universe, and the nature of time and space. General relativity has challenged our traditional understanding of these topics and provided new insights into the universe. The theory of general relativity has been highly successful in explaining the behavior of gravity in the universe, but it is not without its limitations. Over the years, alternative theories of gravity have been developed to address some of these limitations. One of the earliest alternative theories of gravity was modified Newtonian dynamics, or MOND, which was developed in the 1980s. MOND proposed that the behavior of gravity at large distances could be better explained by modifying Newton's law of gravitation, rather than by the curvature of space-time. Another alternative theory of gravity is scalar tensor theories, which modify the theory of general relativity by adding a scalar field to describe the curvature of space-time. This approach allows for a more complex description of gravity, including the possibility of a varying speed of light and deviations from general relativity in the presence of large gravitational fields. Still, another alternative theory of gravity is F-R gravity, which modifies the curvature of spacetime by adding a nonlinear function of the scalar curvature. This theory has been used to explain a range of astrophysical observations, including the observed acceleration of the universe. Despite their potential to address the limitations of general relativity, alternative theories of gravity face significant challenges in explaining observations and experiments. For example, MOND has been challenged by the observed behavior of galaxies, while scalar tensor theories have faced difficulty in explaining the observed behavior of gravitational waves. The development of alternative theories of gravity has not only impacted our understanding of spacetime, but also our understanding of gravity itself. The search for an alternative theory of gravity is ongoing, and advances in both theory and experimentation are likely to provide new insights into the nature of spacetime and gravity. General relativity and quantum mechanics are two of the most successful and well-established theories in physics, but they are fundamentally incompatible with each other. General relativity describes the behavior of gravity on large scales, while quantum mechanics describes the behavior of matter and energy on the smallest scales. The intersection of these two theories is an ongoing challenge in physics and has been the focus of much research. For many years, one of the main challenges in combining general relativity and quantum mechanics is that general relativity is a classical theory, while quantum mechanics is a quantum theory. This means that general relativity does not account for the probabilistic nature of quantum mechanics, nor does it account for quantum fluctuations in spacetime. Despite these challenges, there has been much progress in recent years in understanding the relationship between general relativity and quantum mechanics. One of the most promising areas of research is the development of a theory of quantum gravity, which would describe the behavior of gravity at the quantum scale. One of the leading theories of quantum gravity is loop quantum gravity, which proposes that spacetime is not a continuous entity, but rather is composed of discrete, quantized building blocks. This theory has been successful in describing the behavior of black holes in the early universe, but it still faces significant challenges in explaining observations and experiments. Another leading theory of quantum gravity is string theory, which proposes that the fundamental building blocks of the universe are not particles, but rather one-dimensional objects called strings. String theory has been successful in describing the behavior of particles and forces, but it still faces significant challenges in explaining the behavior of gravity. Despite these challenges, the intersection of general relativity and quantum mechanics remains an area of active research, and advances in both theory and experimentation are likely to provide new insights into the nature of space-time and gravity. Understanding of time is the concept of time dilation. According to general relativity, time moves more slowly in a stronger gravitational field. This means that time passes more quickly in areas of weaker gravity. As a result, Someone standing on the surface of the Earth will age more slowly than someone in a spaceship traveling at high speeds through space. In addition to time dilation, general relativity has also had a significant impact on our understanding of causality. Causality refers to the relationship between cause and effect, and the notion that effects only occur as a result of preceding causes. Prior to general relativity, causality was thought to be an absolute and unbreakable rule. However, general relativity has shown that causality can be impacted by the presence of strong gravitational fields. For example, in a strong gravitational field, light can travel in a curved path, and cause and effect can occur in a different order than what was previously thought. Another impact of general relativity on our understanding of time and causality is the concept of black holes. Black holes are areas of spacetime where the gravitational field is so strong that nothing, not even light, can escape. This means that time and causality are significantly impacted. In the vicinity of a black hole, for example, an observer looking at a black hole from a safe distance would see time appear to slow down for objects as they approach the event horizon, the point of no return. This results in a type of time travel, where the observer would see objects that have fallen into the black hole appear to freeze in time just before crossing the event horizon. Finally, general relativity has also impacted our understanding of the nature of time itself. Prior to general relativity, time was considered to be a universal and unchanging entity. However, general relativity has shown that the passage of time can be affected by the presence of strong gravitational fields. As a result, time is no longer considered to be an absolute and unchanging entity, but rather a flexible and relative concept that is shaped by the presence of matter and energy in the universe. In conclusion, general relativity has had a profound impact on our understanding of time and causality. Through the concept of spacetime, time dilation, black holes, and the flexibility of time itself.
In conclusion, the relationship between space and time and the role in the cosmos and the origin of general relativity has been a fascinating and ongoing journey of discovery. From Albert Einstein's groundbreaking work to the latest develops in alternative theories of gravity and the search of theory of quantum gravity, this topic continues to inspire and challenge us. Whatever we are seeking to deepen our understanding of the cosmos, or to push the boundaries of what we know, the study of space, time, and general relativity will remain a critical and exciting area of exploration. Subscribe if you like this content. Bye guys.